Today we're going to wrap up the chapter on sequences and series, and I'll give you a couple of interesting problems to go through that have to do with sequences or series. The first one is, what if you're asked to write an expression for the following series, and I'm going to ask you to use sigma notation. And it goes like this: 3 minus 6 plus 9 minus 12 plus 15 minus 18, and this is an infinite series. Now this is not arithmetic because the difference between two consecutive terms is not equal. The difference between -6 and 3 is 9, but the difference between 9 and -6 is 15, and the difference between -12 and 9 is -3. So you have something that's not arithmetic. But if you take the absolute value of these terms, it would become arithmetic. So the absolute value of each term becomes arithmetic because the difference between 3, 6, 9, 12 would all be equal to 3. So you'd have a common difference. So when you have a situation like this, but you have alternating signs, positive, negative, alternating signs require a -1 to the power of some value of n, and n is either going to be n, or it's going to be -1 to the n minus 1 power. And that's going to make, when we go through the n values of 1, 2, 3, 4, 5, this -1 raised to the first, third, fifth, and seventh power is going to make the term negative, and this raised to the 0, 2, 4, 6, and any even power would make this term go positive. So what we're going to do is we're going to set up an expression for this, pretending that this is absolute value, pretending that this is an arithmetic sequence. And we're pretending it's arithmetic by using the absolute value of each term. So if we wanted to write a formula for that, the arithmetic formula, the arithmetic sequence formula, an equals a1 plus d times n minus 1. The first term is 3. The difference is 3. So if you distribute the 3 and combine like terms, you have an is equal to 3n. So that would give us our 3, 6, 9, 12, 15, 18 if they were all positive. And what would give us our alternating signs is -1 to the power of either n or n minus 1. So what we're going to do is we're going to take this alternating sign and we're going to tack on a -1 to the power of, it's either going to be n or it's going to be n minus 1, and we're going to test that. If we want to find a1, the first term is equal to 3 times 1, which is 3, times -1 to the 1, which is -1. So if we chose this as n, it's going to give us a -3 here, and we want a +3. So this exponent, instead of being n, it's going to be n minus 1. That would be the adjustment to make the first term positive, second negative, third positive. If this series started with a negative number, then you're going to have this just be -1 to the power of n without the -1. So if we want to use sigma notation, let's say it's an infinite series, so n is equal to 1 up to infinity because it goes on forever, and our expression is 3n, which would give us 3, 6, 9, 12, and then what would give us our alternating signs is -1 to the power of n minus 1. So that's the end of that. And we couldn't find the infinite sum, because this is arithmetic and this would diverge, because the only thing that converges is a geometric series where the ratio is, absolute value of the ratio is less than 1, for our purposes this year anyways. Okay, let's try another one. Let's say we want to write using sigma notation, same instructions as before. We have negative 256 plus 64 minus 16 plus 4 minus 1 plus dot, dot, dot. So this is an infinite series. So this would be similar to the exercises that we did today in class on the worksheet. We know this is geometric, because if you divide any two consecutive terms, you're going to get a common ratio, and this common ratio is equal to negative 1/4. So the nth term of a geometric sequence is a1, negative 256, times r, negative 1/4, to the n minus 1. So that's really all you have to do here, and that will help, that'll alternate your terms. If we wanted to write this in sigma notation, we just say n is equal to 1 to infinity of negative 256 times negative 1/4 to the n minus 1. And if you plug in n equals 1, you get negative 256, which matches the first term. Plug in n equals 2, you would get positive 64. And if I wanted to make that, if I wanted to figure out what the infinite sum is, the infinite sum is a1 times 1 over 1 minus r, negative 1/4, which is negative 256 over 5/4. Flip the bottom, which is a multiplication by 4/5. And 256 times 4 and negative 256 times 4/5 is equal to negative 256 times 4 is negative 1024, and 1 times 5 is 5. So negative 1024 over 5 would be that infinite series. Let's do a third example. Let's say I want you to write in sigma notation 1/2 minus x squared over 4, x to the first over 4, plus x squared over 8 minus x cubed over 16 plus x to the fourth over 32 minus x to the fifth over 64. And that's it. This is not infinite. All right, this is a finite series. So what I like to do is, if I'm asked to write this in sigma notation, because this is not a real common series to write, I like to write the n value underneath, which is the term number. So here's the first, second, third, fourth, fifth, and sixth terms. So I'm going to write a 1, second, third, fourth, fifth, and sixth. And so what I do is I see that the denominator is changing, the numerator is changing, and each one of those can be written as some function of this n value. And I can see here that it goes from 2 to 4 to 8 to 16 to 32 to 64. And I can see this is 2 to the first, 4 is 2 to the second, 8 is 2 to the third, 16 is 2 to the fourth, and on and on. So you should recognize these denominators as powers of 2. So I'll start out with my sigma. And because I have 6 terms, my n value is going to go from 1 to 6. This top number is always, when you have a finite series, not always, but the easiest way to do it is starting with 1 and ending at the term number. And now we have a fraction. The denominator changes according to 2 to the nth power. So that's how I like to start out. Now I'm going to look at the numerator. And we have 1, x to the first, second, third, fourth, fifth, and how does that relate to each one of these n values? Well, they're x to some power of n, and you notice that each one of these powers is 1 less than the n value that I've listed under here. Even this is x to the 0 power. So we can call this x to the n, but it's 1 less than that, so it's actually x to the n minus 1. And then we'll get the x to the 0, first, second, third. This is one of several different correct answers for the sigma notation. But now we have to handle the alternating between negative and positive. So if I put a negative 2 to the nth power, then the very first term would give me a negative 1/2. So I really want to do 2 to the nth power, and how do I get my first term to be a positive number? Like I said, this is one of several different ways. I can get negative 1, and this can go either in the numerator or the denominator, this negative 1 to the power of. And because the first term is positive, I'm going to call this n minus 1. So this would give me a first term that's positive, but a second term that's negative. So this can go here, or it can go here. So I'll just show you another way of writing this. N is equal to 1 to 6 of x to the n minus 1 times negative 1 to the n minus 1. And I can call that 2 to the n on the bottom. Or if I want to write this with the negative 1 to the n minus 1 out in front, or behind the fraction or out in front, it doesn't matter. But it just has to go one place so you can get the alternating signs to go positive, negative, positive, negative. All right. The next thing I want to do is give you a practice on a recursive sequence. So this is really nothing different than what we've done before. And let's say I want you to write the first 5 terms. And I'm going to tell you the first term is 1. I'm going to tell you the second term is 2. So we really have only 3 more to go. So the definition of this recursive series is the nth term is equal to the n minus 1 term squared times the n minus 2 term. So there is the definition. And these are your starting values. So our job is to write the first 5 terms. So the first 5 terms are A1, 2, 3, 4, and 5. And it's a no-brainer for the first 2 because I told you them. Now the third term. Well, the third term is when n equals 3, because this an, the third term is n equals 3. So the third term is the second term, because 3 minus 1 is 2, squared times 3 minus 2 is 1 times the first term to the first power. So the second term squared is 2 squared. The first term is 1. And 2 squared times 1 is 4. So there's your third term. The fourth term is the third term squared times the second term. Well, the third term is 4. The second term is 2. 4 squared is 16 times 2 is 32. Now the fifth term. The fifth term is the fourth term squared times the third term. The fourth term is 32. The third term is 4. And I think I'll have to pull out the calculator. I guess I would let you use a calculator on this if you had to. So the calculator says 32 squared times 4 is 4096. So the first 5 terms are 1, 2, 4, 32, and 4096. The next thing I want to talk about is factorials. Hopefully you remember what a factorial is. You probably haven't done them in a while, but n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 all the way down to 1 until you get to 1. So for example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1. So this is 20 times 6, which is 120. So sometimes factorials are used when we're writing sequences out or when we're trying to find series. And let's say I want you to evaluate this sigma problem. Let's say we have I is equal to 0 to 4, and let's say we have x to the I plus 1 over I factorial. One thing you need to know about factorials is that 0 factorial is equal to 1. So I'm going to have you put that as a little note. 0 factorial equals 1. 1 factorial is also equal to 1. 2 factorial equals 2, and 3 factorial equals 6. So if we wanted to expand that out, we have x to the 0 plus 1 over 0 factorial, which is 1. And then we have x to the 1 plus 1 over 1 factorial, which is 1. Then we have x to the 3rd power over 2 factorial, which is 2. Then we have x to the 4th power over, this is 0, 1, 2, 3 factorials, 3 times 2 times 1, which is 6. And then our last term is when I equals 4. So we have x to the 5th power over 4 factorial is 4 times 3 times 2 times 1. 4 times 3 is 12. 12 times 2 is 24. So there you would have the expanded version of that factorial. I just wanted to remind you of what a factorial was in case you've forgotten it since Algebra 1. The next thing I want to mention is talking about arithmetic sequences. Sometimes you're going to have to find D if you are not given 2 consecutive terms. So that D value is equal to, you can't just subtract the 2 terms because maybe you're given like the 3rd and the 6th term. So what you have to do is you have to subtract the later term minus the earlier term, whatever it is, like the 6 minus the 3rd, and divide it by what the term number is, m minus n. So that's a helpful formula. Let's say, for example, you are given the 3rd term is 12, and you're given the 6th term is 21. And I'm going to ask you to find D. Well, in this little example here, the d value is equal to the sixth term minus the third term, all divided by 6 minus 3, because those are the term numbers. So 21 minus 12 is 9. 6 minus 3 is 3, so the d value is equal to 3. So if I wanted to figure out the formula for that, an is equal to a1 plus d times n minus 1 for an arithmetic formula. Well, if I know the third term is 12 and I know d is 3, then I can just subtract 6 from 12 to get down to the first term. Because of the d value being 3, you just increase by 3 to get to the next, so you can decrease by 3 and by 3 again to get down to the first term. So 6 plus 3 times n minus 1, and if you distribute the 3 and combine like terms, you get 3n plus 3 would be the formula for that sequence if I give you the third and the sixth. And then the very last thing for today and the very last thing for this chapter is if you have a geometric sequence and you're given non-consecutive terms, just like the last example when I had an arithmetic sequence given non-consecutive terms, if you want to find r, the r value, let's say the non-consecutive terms are am and an. Let's say this time the nth term is later than, or it follows am. So the ratio, the r value, the common ratio, is the root of an over am, and then you're going to subtract n minus m. So you're going to get the cubed root or the fourth root or the fifth root, depending on how far apart those terms are, of the quotient of the two terms that you're given. And that looks very complicated, but it's not real. It's not real bad because I wouldn't give you anything where the terms are too far apart. Let's say we have the fourth term is negative 576, and let's say the seventh term is 36,864, and that's in a geometric sequence. And let's say we are supposed to find r, and I will let you use a calculator for this. So since we're given those two terms, we're going to, and it's geometric, we're going to use the root feature. And it's 36,864 divided by negative 576. And the term numbers, I have the seventh and the fourth, so I'm going to do 7 minus 4. So what I really have is the cubed root of, and I'm taking my calculator out, 36,864 divided by negative 576 is negative 64. And the cubed root of negative 64 is the bell, negative 4. So we'll get some practice in class tomorrow on these kind of geometric sequences. And that's it for the chapter.